Hello everyone. In the last video we saw that how increasing the capacitance or increasing the output load of this particular inverter had helped you actually to reduce the glitch. Okay, so let's start from this point. Okay, let's start from this point where we had seen a very low output load and how increasing the output load actually helps to reduce the glitch at the output of this particular inverter. So initially we had a decent output load. Now when we actually increase the output load, you see the glitch head also reduces. If you increase it even more, the glitch head again reduces. And the reason that we identified was the output load capacitance and its behavior. So what is actually happening is when you increase your output load capacitance, you can actually store large amount of charges on that particular capacitance. So under a steady state condition where let's say a logic 1 voltage, let's say you had a logic 1 voltage over here, as it is very obvious from this state. So the state of this particular capacitance was logic 1. What does that actually mean? That actually means that there is huge amount of charge that is getting stored, that is already stored on this particular capacitance. Now when the inverter input sees a transition something like this, and when it sees a fall transition something like this, the inverter is open for an amount of time that is t, and during this t period amount of time, all the charges that is present on this capacitance has to get discharged through this particular inverter, so as to get a glitch, a falling glitch over here. But since the amount of output, since the amount of charge that is present on this capacitor is so huge, this time period, the t amount of time period is just not enough for this particular inverter to discharge all of them. It's like a room. Let's say you have a very big room, and since you have a very big room, you can accommodate lot amount of people over there compared to a small room. And when you want to release, when you want to empty out that particular room, a large room will take a large amount of time to empty out in compared to a small room. Similarly, a large capacitance is like a large room. You have already accommodated huge amount of people, or you have already accommodated huge amount of charges on this particular capacitance. Now during this period of time, when you see a glitch, during this finite period of time, when you see a glitch, your inverter is open, and that amount of time that for which the inverter is open is just not huge enough for all the capacity, for all the charges to discharge through this particular inverter. Okay, and as a result of that, whenever you see an high output load capacitance, you see that has got a direct impact, or direct impact on the glitch height. Basically the load capacitance has got a direct impact on the glitch height. Okay, so this was a amount of literature that a justification in the form of literature, that how the output load capacitance actually helps to reduce your glitch. And the other, on the other hand, if this glitch is not propagating through this particular inverter, this glitch is no more a hazardous glitch for us, or it's no more an unsafe glitch for us. This glitch can be considered as a safe glitch. Okay, even the glitch is of so big width and so big height, it's still a safe glitch because it just can't propagate through this particular inverter, and because of the how output load capacitance. So there could be other impacts of having a output load capacitance, of having high output load capacitance. For example, you might just face huge transition time that might lead to delay and all those things. So there are impacts of high output load capacitance, but we are seeing a positive impact of this particular output load capacitance is that you can minimize the glitch. So the output load capacitance should be optimal enough and not huge enough, and not even small enough. Okay, it should be an optimal value. So this is just a technical representation of the analogy or of the literature that we gave at the a few minutes back. So output capacitance, as you increase your output capacitance, your output charge also increases, and as a result of that, the amount of time, that is the amount of discharging current that is required. Discharging current is nothing but the change in the output charge divided by amount of time for which your window is open, basically for which your inverter is open. So the requirement of the discharging current becomes very high, because you have dt which is very short, which is very small, you have output load capacitance which is very high, and as a result of that, the q is very high. So the amount of discharging current that is required, the flow of charge is nothing but the flow of current. So amount of discharging current that is required during this finite amount of time is very high, and the inverter is just not able to fulfill that high amount of discharging current requirement. And as a result of that, you see a very low output glitch. So this is a technical representation of the literature that we saw like few minutes back. Okay. So now what we'll do is we'll take this glitch and we'll put it in the AC noise curve and try to conclude on few things. So the first thing that we will be concluding on this part is whether this glitch is able to propagate or not. If this glitch is able to propagate, it becomes a potentially unsafe glitches for us. And if this particular glitch is not able to propagate, it's a safe glitch for us. And so now, as we have talked in some time from now, what are the deciding factors for this? One was the width and one was the height. So based on width and height and placing this glitch on the top of this particular AC noise curve, we identified this as a potentially unsafe glitch. But now looking into one more parameter, that is capacitance, that is output capacitance, we again came to one more conclusion, and that is, will this glitch be able to propagate or not will be decided, or it depends upon the noise width, noise height, as well as the output load capacitance. So this is the third parameter, and very important one as well, to decide whether this particular glitch is able to propagate or not. Okay, and this output load capacitance sometimes becomes a deciding factor towards the end days of the tape, or whenever we are in a very critical situation in our deliverables. This particular concept becomes very important, because if we know that when we increase our output capacitance, there is a very less chance of the glitch getting propagated, and hence that glitch might just not impact our existing behavior. So this is a very important conclusion that we had made over here. Okay, so that was about the glitch and the dependencies on which the glitch will have. It will be decided on the noise width, or the glitch width, the glitch height, and the output load capacitance. These are the three important factors on which this will be decided. Okay, next what we'll be looking into what if there are multiple aggressors. So when we say multiple aggressors, we actually mean that we have a single victim over here, and there are multiple nets that are impacting this particular victim. So let's try to get a diagrammatical representation of the same. Let's say we have this aggressor A1 which is impacting the victim V. This is the same situation that we had like few in the couple of lectures back. So this is the same scenario. We have this victim, we have this aggressor, and we have a mutual capacitance. Let's call it CM1. Now let's say this design is very congested, and there is one more aggressor which is sitting very close to this particular victim, and that let's call that aggressor as A2. And the mutual capacitance between the coupling capacitance between A2 and V, let's call it as CM2. Okay, so this design is even more heavily congested, that we see even more number of aggressors over here. So let's say we see one more aggressor A3. This will have a minimal impact on the victim net V, but still it will have some impact on the victim V. And let's call that aggressor as A3 and the victim as V, and the mutual capacitance between A3 and V as CM3. The mutual capacitance will be CM3. Okay, and to make things even more complex, let's add one more aggressor over here. So we have 4 aggressors and a single victim net. So what we have to do is we have to do a smart analysis over here, rather than computing the impact of each and every aggressor on this particular victim. We have to come up with a solution that will analyze all of this particular aggressor at the same time, that will analyze the impact of all the aggressors at the same time on the victim net. There are multiple things that will be saving over here. First is the amount of time that will be spent on analysis, and the amount of aggressors, just if the number of aggressors just gets blowed up. So we will be able to bring the number of computations over here to very minimal value. So let's try to identify that particular method of analyzing a victim net with multiple aggressors. We'll try to come up with some solutions, with some optimal solution to, and with some optimistic solution or a pessimistic solution, or basically a solution to solve this kind of problem statements. So let's try to look into all this in the next video. Thank you.